All right. We wait. What happened? Oh yeah, here we are. Let's go. I'm not here today. Obviously, you can tell I'm not here. We're talking about 4.7. Sorry for that little pause there for a minute. So our explorer today talks about a swimming pool holding 21,000 gallons and is being filled by a garden hose at 300 gallons per hour. That's a quick filling garden hose there. Okay. The volume of the water in the pool is a function of time that the hose has been running. So volume equals rate times time. So this first one, the volume is going to be rate times time. Our rate is 300. And let's multiply that by 1 to find my volume to get 300. All right. I'd like you to pause and just fill out the rest of this table. Go ahead. All right. And there we go. This is what I got. Be careful. Okay. Some of us, we jump from 3 to 5. All right. We skip 4, right? We skip 4 hours. So be careful when you made your calculations. We jump from 5 to 10, 10 to 20. So I want you to look at this. I'm going from 1 to 2, I go from 300 to 600. From 2 to 3, I go from 6 to 900. From 3 to 5. From 5 to 10, I go from 1,500 to 3,000. From 10 to 20, et cetera, et cetera. All right, so it says, right in part B, it says write a function that models the relationship between the volume and time. In this scenario, is the function linear? So it gave us the function already. All right, volume equals rate times time. So in this case, volume equals 300. That was our rate times time, or h for hours. Okay, is it linear? Yes, this is linear. Yes, it is. Okay, you can tell. How do I tell that this is linear? Okay, I can tell by looking at this table here. I have a constant rate of change. I'm going up by 300 every time. If I had included 4 would have been 1,200, then 1,500. All right, I'm going up by a constant rate of change. You could also do that. You could also find your slope. You can do it that way too. Okay. Part C, for each line of the table, find the quotient, the volume divided by time. All right. What do you notice about this quotient? How does this value appear in the equation? So if I do the volume divided by the time in the first row, I'll do 300 divided by 1, and I get 300. If I do the second row, I do 600 divided by 2, and I get 300. If you do the third row, 900 divided by 3, I get 300. If I do the whatever row, okay, how about this row? 10 or 3,000 divided by 10, I get 300. What do you notice about this quotient? It's 300 every single time. Okay, it's 300 every single time. Where does it appear? 300 is a slope. Is the rate or slope? Both quantities in the table are increasing. Specifically, whenever time doubles, the volume also doubles. How do I notice? Time is doubling. 1 to 2, my time doubled. Okay. 5 to 10, my time doubled, and the volume went from 15 to 3,000, so it also doubled. Conversely, or similarly, when the time triples, the volume also triples. But I'm sure you could have, you kind of knew that too, didn't you? Didn't you notice? All right, so what are we talking about today? Today we're talking about direct variation. All right, direct variation. Can you recognize direct variation on a table, an equation, a graph? Can you interpret the constant of variation? And do you know how to solve? All right, let's keep going. So direct variation, to me, this is very similar to y equals mx plus b, except it's all it is y equals mx plus 0. B is always 0. The y-intercept is always going to be 0 when we're talking about direct variation, okay? When we talk about direct variation, we want to always find our constant, Okay, we're used to this term. We're used to finding k, but we've always called k our multiplier. So that's another way to think about it. K equals the multiplier. All right, and that's how we thought about it in the past, and that still remains true when we talk about direct variation. So what else? The constant of variation. Let's talk about, if we look at direct variation, how it relates to our explore problem. So if we go back here, all right, our multiplier, our constant of variation, as the book is calling it, but it means multiplier, it's the same exact thing, would be 300 here. All right, 300 is our multiplier. Because every time, see, for this one, we're used to our multiplier being between 0 and 1 pretty much, right? Or greater than 1. We're not used to these huge numbers. Now we're going to start to deal with huge numbers. So it talks about direct variation being a specific type of relationship, of linear relationship, okay, in which y is a non-zero multiple of x, that is, y equals k times x. Slope is the constant of variation. This is all just another way of talking about slope, all right, and how it relates. But you have to recognize that b is always 0 in direct variation. We always have a y-intercept of 0. Okay, if we look at a graph and the y-intercept is not 0, let's say our line was like this or like that, those would not be examples of direct variation, okay, because the y-intercept is not 0, all right? Using the table, write an equation that represents y as a function of x. Does y vary directly with x? If so, find the constant variation. All right, well, what did I do in the explore problem to find that 300? I divided all of my y values by their corresponding x values. No, 3010. All right, 602. Okay, so let's try that in this table. I want you to divide 14 divided by 4. 17.5 divided by 5. All of your y values, divide them by your x values. I would like you to do that right now and tell me and figure out and see if. Hey, look, we get the same thing. It's 3.5. Okay, it's 3.5 when you divide. I divide all my y values by my x values. You recognize that now, in the past, we've talked about, our rate of change being change in y over our change in x. Now it's a little bit different. Okay, we're talking about dividing y by x for all of these. So does y vary directly with x? Yes, if so, state the constant of variation. Well, y, here's what our equation would be. Y equals 3.5x. Our constant, our multiplier, is 3.5. Questions? Okay, let's keep going. For each graph, determine if it shows direct variation. If it does, state the constant variation. If it does not, explain why. Well, look at part A. There should be alarms going off in your head here, alarm bells. Holy buckets, that can't be true. Why can't that be true? Great question. So I'm happy you asked it. I know you were thinking the same thing. Look here, our y-intercept. Look at our y-intercept. So this would be a no. Y-intercept isn't 0. Our y-intercept is 6 here, it needs to be 0. All right, so that should be a dead giveaway here. Look, this is a yes. All right, what's our constant of variation? Our constant of variation here is, well, if I start at 0, what's my next point? Looks like my next ordered pair is 5, which means I go up 5 over 1. So my equation is y equals 5x, or my constant, or my multiplier, is 5. All right. This one, oh look, the y-intercept is 0 again. So this is a yes. My next point to the right of 0 is right here. Down and over, I go down 3 over 1. So k equals -3. This is a no. No, it's not linear. This is the square root function. If it's not a straight line, it can't be direct variation automatically. That rules it out. All right. So this next example, we can use direct variation to solve direct variation problems. Okay. Of course, that makes sense to me, obviously. So suppose y varies directly with x, and the order in which they write that is important. Y varies directly with x. That means y equals k times x. Whatever comes second is being multiplied. Whatever comes first is by itself. So one way to solve direct variation problem is to use direct variation model and find the constant of variation. So how am I going to do that? So what they're doing here is they're using their information here to find our k value, our multiplier. All right, well, if y is 8 and x is 2, then the constant is 4. Now, you might be able to calculate that in your head. How would you calculate that in your head? You would just do 8 divided by 4, or excuse me, 8 divided by 2. Okay? Now, the second part of the question says, find y when x is 4. Well, our multiplier is 4. That means y has to be 16. 4 times 4 is 16. All right? Because x is 4, I just multiply that value by 4 to get y. Okay? You could do this a different way. It says, last week, notice the graph is a direct variation model of y equals 4x, passing through these 2 points. We can also solve this by using a proportion, and then it goes on to explain more using your y and x values here. That's true. You can do that. It's not, like it can help sometimes. How would I do it? I would probably do it this way. I would just think about it algebraically. But some of us are visual people. Okay. Wonder what other way I could think about it is, well, if you compare your x and y values here, or excuse me, your x values. X was 2 and then x was 4. So I doubled 2 to get to 4. Well, it only makes sense that I also double y. That's how you get 16. 8 times 2 gives you 16. Same kind of idea. Notice in the last example, okay, look, it says right here, x doubles from 2 to 4. Since y varies directly, y and x vary directly, y also doubles. So 2 times 8 gives you 16. That's also true. When possible, you just kind of otherwise solve it, and yada, yada. Okay, for sure. Let's keep going. What do we got? Number 4. Suppose A varies directly with W. So right away, I know that A equals KW. All right, when A equals 4 when W equals 8. So A is 4 when W is 8. So if I divide by 8, that means K equals 1/2. Find the value of K. Oh, well, I just did that. Write a direct variation model with the constant of variation. So y equals 1/2 W. Part B, graph the variation model. Well, I know that I'm going to start at 0, 0 always, and I have 1/2 as my slope, so that's up 1 over 2, up 1 over 2, and I can do the same thing, down 1, left 2, down 1, left 2, and then roughly connect the dots. Oh, it's almost time to go. Find A when W is 6. So I have this equation, y equals 1/2 W, or excuse me, A. So I do 1/2 times 6. So then A would be 3. How else could I do that? Well, if W is 6, I could have looked at my graph here too and just kept counting until I hit 6. Oh, look, that was actually the next point I would have graphed. This ordered pair is 6, 3. It's another way you can do it. I prefer to just plug it in like that, okay? But you can do it either way. All right, there's a lot of different ways. What else could I have done? Well, I could have found out the ratio of 8 over 6 and compared that to the ratio of 4 over whatever. Here's how it works. All right, it tells you a lot of it. Option 1, talking about not using proportions. Option 2 uses proportions. Option 1, find K and write a model. I think option 1 to me is going to make a little bit more sense to us. Okay, that'll make a little bit more sense to us. All right, John's pay varies directly with the number of hours he works. When he works 20 hours, he gets paid $240. How much does he make if he works 32 hours? What's the constant variation? Okay, so John's pay, so pay equals constant times hours. Well, if his pay is 240 and the number of hours he works is 20, let's find our multiplier. K equals 12. So what is the constant of variation? K equals 12. Boom. What is its significance? Well, in this problem, okay, if I think about this, in terms of the job itself, how much does he make? Or I skipped the question. How much does he make if he works 32 hours? Well, I would do pay equals 12 times 32, which ends up being 384. 84. Well, what is this 12? 12 is our hourly rate. One particular type of direct variation is joint variation. It's the same idea, except it involves 3 or more variables. All right? This means y varies jointly with both x and y. Suppose m varies directly with a and b, so k times a, b. Remember, whatever comes first is by itself. That's the most important thing there. Whatever comes first is by itself. All right? What does it say? So it says m is 102, a is 2, b is 3. Find m when a and b are both 6. So I'm going to use that first part to help me find my k value. And that's the first step more times than not. So 102 equals 6k. Divide both sides by 6. K equals 17. All right. So our next part says find m when a and b are both 6. Do 6 times 6 times 17. 36 times 17, I got 6. Going. Simple interest. This will be our last problem for today. Simple interest, I'll start with I, equals, varies jointly with the amount invested, so here's my multiplier, times P, the interest rate, so R, and time T. Write a variation model assuming a constant interest rate of 3.5%. Remember, that is 0.035. And find the interest earned if 2,000 is invested for 4 years. I made a mistake here. This R is, which makes sense. This R is our multiplier. All right, this R is our multiplier. R is our multiplier times PT. That makes that is the amount invested with the interest rate. R is the multiplier. R is our K value. That's what we want to use. If initial amount invested is 2,000 over 4 years, just like that. And you should get 280. So this equation, the first part, this equation would be I equals 0.035 PT. That's what the equation would be using the values, and this is how much interest we would have. We deposited $2,000 over 4 years. All right. We're going to call it there. Okay. We're not going to do the connection part. I think we have a pretty good handle on direct variation, or we might, I don't know. I can't see your faces. I'm not even there, so I'm just going to take a guess. But I think we should be all right. Remember, we talked about find direct variation from a graph, table, or equation, and other models as well.